February 10th, 2009. 490 miles above Siberia. Two satellites, one American, one Russian, traveling at a combined speed of 26,000 miles per hour, collide head-on. The impact lasts a fraction of a second. The aftermath? Still unfolding 16 years later. In that microsecond, two satellites became 2,000 pieces of shrapnel, each piece a bullet traveling faster than any rifle ever made. Each piece a potential trigger for the next collision, and the next, and the next. This is what scientists call Kessler Syndrome, a cascading collision scenario named after NASA physicist Donald Kessler, who predicted it in 1978. He warned us that once a chain reaction starts in orbit, it doesn't stop. It accelerates exponentially. Right now, at this exact moment, there are 34,000 pieces of tracked debris larger than a softball orbiting Earth, another 130 million pieces too small to track, and approximately 8,800 active satellites. Those satellites are worth $3 trillion. That's not their construction cost, that's the value of the global economy they support. Banking transactions, navigation systems, weather forecasts, military communications, your ability to stream this video. All of it depends on machines circling overhead at 17,000 miles per hour in an environment where a paint fleck can punch through titanium. And here's the thing nobody wants to say out loud. We've already started the countdown. On November 15, 2021, Russia fired a ground-based missile at one of its own defunct satellites. The explosion created over 1,500 trackable fragments and hundreds of thousands more too small to see. Astronauts on the International Space Station had 2 hours to seal themselves into escape modules. The debris cloud passed within miles of the station. It's still up there, all of it, and it'll stay up there for decades. This wasn't an accident. This was a weapons test, a demonstration that any nation with a missile can turn orbit into a minefield. And once you pull that trigger, you can't put the bullets back in the gun. Welcome to the most expensive, most ignored, and most inevitable disaster in human history. A disaster we're creating one launch at a time. A disaster that could end in 90 minutes and take 50 years to fix. This is Kessler Syndrome, the $3 trillion apocalypse nobody's talking about.
Let's start with something most people never think about. Right now, above your head, there's a highway. Actually, there are several highways. Invisible lanes of orbital space where satellites circle the Earth at precise altitudes and speeds. Low Earth orbit, 160 to 1,200 miles up. This is the fast lane. Satellites here orbit every 90 minutes. The International Space Station, spy satellites, Earth observation, and increasingly mega-constellations like Starlink. Medium Earth orbit, 1,200 to 22,000 miles up. This is where GPS lives. 24 satellites giving you turn-by-turn directions and precision timing for literally everything that requires synchronization. Banks, power grids, cell towers. And geostationary orbit, 22,236 miles up, the penthouse suite of space. Satellites here orbit once every 24 hours, perfectly synchronized with Earth's rotation. They appear to hover over one spot. This is where the big money lives. Communication satellites, weather satellites, military early warning systems. Here's what makes this highway unique. There are no exits, no rest stops, no breakdown lanes. If something goes wrong up here, you can't pull over, you can't slow down, you definitely can't stop. And unlike a highway where everyone goes roughly the same direction, space orbit is three-dimensional chaos. Satellites in polar orbits cross paths with satellites in equatorial orbits. Higher orbits move slower, lower orbits move faster. It's less like a highway and more like a three-dimensional game of chicken played by robots at 17,000 miles per hour. So how many vehicles are on this highway? As of 2025, approximately 8,800 active satellites, about 3,000 dead satellites, 34,000 pieces of trackable debris larger than 10 centimeters, 130 million pieces smaller than 10 centimeters that we can't track but we know are there. And here's where the sarcasm starts. We're about to make this much, much worse. SpaceX wants 42,000 Starlink satellites, Amazon's Project Kuiper, 3,236 satellites. OneWeb has launched over 600. China just announced plans for 2 mega-constellations totaling 13,000 satellites. By 2030, we could have 60,000 active satellites in orbit. For context, that's more than we launched in the entire history of spaceflight from 1957 to 2020. Now you might be thinking, space is big, really big. Surely there's room for everyone. Allow me to introduce you to the mathematics of orbital crowding. See, not all orbital space is created equal. There are sweet spots, altitudes where satellites can function optimally for their mission. For internet constellations, that's 340 to 550 miles up. For GPS, it's exactly 12,550 miles. For geostationary communications, it's precisely 22,236 miles. And here's the problem. Orbital mechanics is deterministic. If you want your satellite to do a specific job, it needs to be at a specific altitude, traveling at a specific speed. There's no flexibility. It's physics. So when SpaceX puts a satellite at 340 miles altitude, and OneWeb puts one at 342 miles, and Starlink launches another at 338 miles, they're all sharing the same narrow band of orbital space. How close do they get? Let me show you some numbers that should keep you up at night. In 2020, 1,600 close approaches requiring evasive maneuvers. 2021, 3,800 close approaches. 2022, 6,200 close approaches. 2023, over 10,000 close approaches. That's not a trend, that's a crisis in fast forward. And here's where it gets absolutely ridiculous. SpaceX now performs over 25,000 collision avoidance maneuvers per year. That's 68 per day, nearly 3 per hour. Think about that. Every 20 minutes, somewhere in orbit, a satellite is firing its thrusters to avoid hitting something else. And that's just Starlink. Every satellite operator is playing the same game, constantly calculating trajectories, constantly adjusting. One mistake, one miscalculation, one thruster failure, one missed warning, and you have a collision. Which brings us back to February 10, 2009. Iridium 33, an American communications satellite, and Cosmos 2251, a defunct Russian military satellite, collided at 11.7 kilometers per second. The impact released energy equivalent to an exploding bus. In 1/1000th of a second, two satellites became 2,300 trackable fragments. Estimates suggest another 300,000 too small to track were created. Those fragments didn't just sit there, they spread out along the entire orbital path. Within hours, they formed a ring of debris around Earth. Within weeks, gravitational perturbations and atmospheric drag spread them into a cloud. 16 years later, over 1,500 pieces are still being actively tracked. They'll stay in orbit for decades. Every one of them is a loaded gun pointed at every other satellite in that orbital shell. The International Space Station has had to dodge Iridium Cosmos debris 29 times since 2009. 29 times astronauts have sealed themselves into their spacecraft, ready to evacuate, while a bullet traveling at 17,000 miles per hour passes within a few miles of the station. And that's from just one collision, one accident between two satellites. Now let me tell you about what happens when nations do it on purpose. Anti-satellite weapons tests. the ultimate act of orbital vandalism. China, 2007, destroyed the Fengyun 1C weather satellite, created over 3,500 trackable fragments. United States, 2008, shot down USA-193, a failed spy satellite, created about 174 trackable pieces, most of which deorbited within months due to low altitude. India, 2019, destroyed Microsat-R in Mission Shakti, created about 400 trackable fragments. Russia, November 15, 2021, destroyed Cosmos 1408 with a ground-based missile, created over 1,500 trackable fragments and an estimated hundreds of thousands of smaller pieces. That last one? That's the one that nearly killed the crew of the International Space Station. Reckless is one word for it. Insane is another. Catastrophically short-sighted also comes to mind. The debris from that single test will remain in orbit for years. Some pieces will stay up there for decades. And every single fragment is a loaded gun pointed at every other satellite in that orbital shell. This is the spark, the match in the gasoline-soaked room, the first domino in a chain that could destroy everything we've put in orbit. And the terrifying part, we've already struck the match. We're just waiting to see if the fire catches. Because every day, satellites are dodging debris from these tests. Every day, we're rolling the dice, and eventually, statistically, inevitably, we're going to roll snake eyes. So let's talk about what happens when we do. Let's talk about the mathematics of doom. Let's talk about Kessler Syndrome.
1978. A NASA orbital debris scientist named Donald Kessler published a paper with a title that should have made headlines, but instead disappeared into academic obscurity. In it, Kessler laid out a scenario that sounds like science fiction, but is actually just science. He described what would happen if the density of objects in low Earth orbit reached a critical threshold. His conclusion was elegant and horrifying. At a certain point, collisions would become self-sustaining. Each collision creates debris. Debris causes more collisions. More collisions create more debris. Feedback loop, exponential growth, unstoppable. He called it a collisional cascading scenario. Everyone else now calls it Kessler Syndrome. And here's the truly disturbing part. Kessler didn't predict this would happen in some distant future. He predicted it would begin within decades, and in particular orbital shells, specifically between 300 and 600 miles altitude, it might have already begun. Let me break down the mathematics in terms anyone can understand. Start with a stable orbital shell, say 10 satellites and minimal debris. Collision probability is low. Everyone's relatively safe. Add more satellites, 50, 100, 500. Collision probability increases, but it's manageable. Operators can track objects, perform avoidance maneuvers, generally keep things safe. Now here's where it gets interesting. There's a threshold, a tipping point, where the number of objects and the collision probability cross a critical line. Above this threshold, the rate of new debris creation from collisions exceeds the rate of debris removal from atmospheric drag and active cleanup. Once you cross that line, the debris population grows on its own. Even if you stop launching satellites entirely, the debris keeps multiplying. And the terrifying question is, have we already crossed it? Depends who you ask. Some models say we're close, but not quite there. Others say we crossed the threshold in certain orbital shells back in 2007 when China blew up Fengyun 1C. That single event dumped 3,500 trackable pieces and an estimated 150,000 smaller fragments into one of the most densely populated orbital regions. And here's where the sarcasm really kicks in. That debris isn't going away anytime soon. At 850 miles altitude, atmospheric drag is minimal. Some of those fragments will stay in orbit for 100 years. The smaller pieces, the ones we can't track, will stay up there even longer. So for the next century, every satellite that passes through that altitude is playing Russian roulette with Chinese space junk. But let's get specific about what cascading collision actually means, because this is where the nightmare really unfolds. Imagine this: a defunct Russian satellite, Cosmos 1408, let's say, since we've already blown it up, collides with an active Starlink satellite at 17,500 miles per hour. Sound, massive impact, metal tearing, explosive decompression. That collision creates approximately 2,000 trackable fragments. Each piece carries enormous kinetic energy. A 10-centimeter fragment hitting another satellite releases energy equivalent to an exploding hand grenade. Now, follow just one of those fragments. It's traveling at 17,000 miles per hour in a polar orbit. Within 45 minutes, it crosses the equator, where thousands of other satellites orbit. Probability of hitting something on the first pass? Low, maybe 1 in 10,000. But it makes 2 passes per orbit. That's 32 passes per day, 11,680 passes per year. And remember, that's just one fragment. There are 2,000 of them from this collision, all with different orbits, all crossing paths with different satellites. Now, run the probability calculation. 2,000 fragments, each making thousands of orbital passes per year, each pass creating a chance, however small, of another collision. Statistical models suggest another collision becomes likely within 1 to 3 years. And when that happens, you don't have 2,000 fragments, you have 4,000, then 8,000, 16,000. This is exponential growth. This is why it's called a cascade. This is why it's unstoppable once it starts. So, how long does it take? From first collision to complete orbital chaos? Computer models vary. Some say 6 months, others say years. But the consensus for a full-blown cascade in low Earth orbit? Between 90 minutes for initial cascade to 6 months for complete orbital shell contamination. 90 minutes to destroy an entire orbital shell, 6 months to make low Earth orbit unusable for decades. Let me paint you a picture of what that actually means. Day 1, 0900 hours, normal operations. Satellites are functioning, communications are stable, everything's fine. 0915 hours, collision detected. Starlink satellite destroyed by debris. Ground control loses signal. 0930 hours, debris cloud detected. Over 2,000 new fragments. Tracking systems overwhelmed. 1100 hours, second collision. OneWeb satellite destroyed. Another 1,500 fragments. 1,300 hours, third collision, fourth collision. Cascade initiating. 1,400 hours. The Pentagon's space surveillance network stops issuing individual warnings. There are too many. 1,430 hours. International Space Station crew ordered to Soyuz and Dragon capsules. Prepare for emergency evacuation. 1,800 hours. 72 satellites destroyed. Collision rate accelerating. 2,100 hours. The cascade is now self-sustaining. 340 satellites destroyed. Over 100,000 trackable fragments created. Day 1, 2,400 hours. Low Earth orbit is now a debris field. Satellite constellations reduced to orbital shotgun blasts. The highway has become a demolition derby. And this is just the first 24 hours. Week 1, 2,000 satellites destroyed or damaged. GPS degraded globally. Internet constellations shredded. Earth observation systems blind. Month 3, 5,500 satellites lost. Fragments numbering in the millions. Every orbital shell between 300 and 800 kilometers is contaminated. Month 6, low Earth orbit is effectively unusable. The debris density is so high that any new satellite launched would be destroyed within days, if not hours. And here's the part that should terrify anyone who understands what we've built our civilization on. Once a Kessler cascade begins, there's no way to stop it. No abort button, no emergency brake. You can't negotiate with debris. You can't call a ceasefire with physics. All you can do is watch as decades of space infrastructure is reduced to an orbital junkyard. $500 billion in satellites destroyed, $1.2 trillion in economic damage from lost services, $2 trillion in replacement costs, $3 trillion in total economic impact. $3 trillion. That's the current estimate for a full Kessler cascade in low Earth orbit. But money is just numbers. Let's talk about what actually breaks. GPS stops working, not degrades, stops. Your phone can't find you. Airplanes can't navigate. Ships lose positioning. The military loses precision guidance. The financial system loses time synchronization. Every stock trade, every financial transaction, every ATM withdrawal depends on GPS timestamping for synchronization. When GPS dies, the financial system has about 4 hours before critical systems start failing. Power grids use GPS for timing synchronization across hundreds of generating stations. Lose GPS, and you're manually coordinating a system designed for automated precision. Blackouts become likely. Internet constellations, Starlink, OneWeb, Kuiper, gone. 3 billion people in underserved regions lose connectivity. Weather satellites, blind. No more hurricane tracking from space. No wildfire detection. No crop monitoring. No climate observation. Military communications and reconnaissance satellites, destroyed. Strategic early warning systems, gone. Command and control networks, disrupted. And the International Space Station? Evacuated, abandoned, left to eventually spiral down into a fiery re-entry because the debris field is too dangerous to approach for resupply missions. 25 years of international cooperation, $150 billion in investment, the crown jewel of human presence in space, abandoned because we couldn't keep our orbital neighborhood clean. So, let's address the obvious question. Can't we just clean it up? In theory, yes. In practice, let me introduce you to the horrifying economics of orbital cleanup. Current cost to deorbit one large satellite is $100 to $200 million. Number of defunct satellites currently in orbit? 3,000. Cost to remove all defunct satellites is $300 to $600 billion. And that's just the satellites. That's not the 34,000 tracked debris pieces. That's definitely not the 130 million untracked fragments. The technology exists, barely. European
space agencies tested a net capture system. Japan tested a tether. Both missions had mixed results. But even if the technology was perfect, the economics are impossible. Launching one cleanup mission costs hundreds of millions. You'd need thousands of missions to make a dent in the debris population. NASA's entire annual budget is $25 billion. ESA's is about $7 billion. Even combined, dedicated entirely to debris cleanup, they couldn't remove debris fast enough to prevent a cascade once it starts. Because here's the sick joke. While you're cleaning up old debris, new collisions are creating more debris faster than you can remove it. It's Sisyphean, literally. So we come to the only logical conclusion. Prevention is the only viable strategy. Which brings us to what's actually being done right now to prevent this nightmare scenario. Space surveillance networks, collision avoidance protocols, design standards for satellite deorbiting, traffic management systems. It's working, barely. We're performing over 30,000 collision avoidance maneuvers per year across all operators. We're tracking 34,000 objects. We're issuing warnings. But we're not addressing the fundamental problem. There are too many objects in too little space, and we're adding more every day. 2024, 2,500 satellites launched. 2025, projected 3,000 satellites. 2030, projected 8,000 to 10,000 satellites per year. We're not just approaching the Kessler threshold, we're sprinting toward it. And the absolute worst part? The people making the decisions to launch these mega-constellations aren't stupid. They know the risks. They've read the papers, they've seen the models, they understand Kessler Syndrome. They just don't care. Or more accurately, they've calculated that the profit from launching comes before the cost of catastrophe, and catastrophe is someone else's problem. Because here's the sick economics of it. If SpaceX doesn't launch Starlink, someone else will capture that market. If Amazon hesitates on Project Cooper, they lose first-mover advantage. If China waits, the US dominates. It's a race to orbit, a gold rush. And in a gold rush, environmental consequences are always ignored until it's too late. We've seen this movie before. We know how it ends. The difference is, when you destroy a landscape, nature eventually recovers. When you destroy an orbital shell, physics determines the timeline. And physics says decades to centuries. Which brings us to the next question. What happens down here when everything up there breaks? What happens to our $3 trillion space-dependent economy when space itself becomes inaccessible?
Let me tell you a story about a day that hasn't happened yet, but statistically probably will. 6:47 a.m. Eastern Standard Time. An asteroid tracking satellite operated by the European Space Agency detects a collision between two pieces of debris at 550 kilometers altitude. The impact isn't remarkable by itself. Debris hits debris occasionally. Usually it's small fragments. Usually it's manageable. This time, it's a defunct Russian military satellite hitting a fragment from the 2009 Iridium Cosmos collision. Combined mass, 1,200 kilograms. Impact velocity, 14.7 kilometers per second. Energy release, equivalent to 127 kilograms of TNT. Result, 1,847 trackable fragments, estimated 200,000 sub-centimeter pieces. 6:52 a.m. The U.S. Space Force's Space Surveillance Network issues a debris event alert, Level 3, significant. All satellite operators notified. 7:15 a.m. Starlink Operations Center in Hawthorne, California begins calculating conjunction assessments for their 4,200 active satellites. Result, 127 satellites now have collision probabilities above the 1 in 10,000 threshold, requiring evasive maneuvers. 7:30 a.m. Automated collision avoidance systems engage. 127 Starlink satellites begin maneuvering. This is more than they've ever moved simultaneously. 7:35 a.m. OneWeb issues maneuver commands to 43 satellites, Planet Labs to 29. China's satellites begin maneuvering, though details aren't shared publicly. 7:45 a.m. The first problem emerges. With hundreds of satellites maneuvering simultaneously, the predictive models start breaking down. When one satellite moves, it changes collision probabilities for others. When hundreds move simultaneously, the cascade of prediction changes overwhelms computational capacity. This is the orbital equivalent of every car on a highway suddenly swerving at once. You might dodge the first obstacle, but you can't predict what everyone else is going to hit. 8:14 a.m. The second problem. One Starlink satellite fails to maneuver. Thruster malfunction. It stays in the path of oncoming debris. 8:16 a.m. Collision. 8:17 a.m. Starlink loses telemetry from satellite 3847. No response to commands. 8:18 a.m. U.S. Space Force radar confirms debris event. New cloud detected. 8:21 a.m. Preliminary count, 400 plus new trackable fragments. 8:34 a.m. OneWeb satellite 0247 collision. Another debris cloud. 8:51 a.m. Chinese satellite collision. Details unknown. Communications blackout from Chinese Space Agency. I could walk you through every hour of the next 3 days, every collision, every failure, every moment the cascade accelerates. But let me skip ahead to what matters to everyone on the ground. 7 days after the initial cascade begins, most people still think it's a technical problem that will be fixed. Satellite companies are issuing statements about temporary service disruptions. News coverage is minimal. It's a space story after all, not something that affects daily life. Except it affects everything. GPS is the first thing people notice, not because it stops completely, some satellites in medium Earth orbit are still functioning, but because accuracy degrades dramatically. Your phone still shows your location, it's just wrong by half a mile. Good luck navigating city streets when your GPS thinks you're 6 blocks away. Delivery services start experiencing delays. Routing optimization algorithms depend on precise GPS. When precision drops, efficiency craters. Commercial shipping slows down. Ships can still navigate using backup systems, but precision port entry becomes difficult. Docking times increase. Supply chain delays begin. Aviation is hit harder. GPS approaches are disabled at many airports. Older navigation systems are reactivated, but they're slower, less precise. Flight times increase. Capacity decreases. Delays compound. 2 weeks into the cascade, the financial system starts showing strain. High-frequency trading algorithms depend on GPS time synchronization accurate to nanoseconds. When GPS timing becomes unreliable, trading systems start failing consistency checks. The New York Stock Exchange implements temporary trading halts to verify transaction timing. The London Stock Exchange follows. Tokyo, Hong Kong. Within 48 hours, global equity markets are operating on emergency protocols. ATM networks start experiencing intermittent failures. Not everywhere, but enough to cause concern. Bank branches see increased traffic, lines form. Power grid operators switch to backup timing systems, but the North American grid depends on GPS for synchronization across 3,200 separate utilities. Manual coordination is possible, but fragile. Minor blackouts begin in areas where grid coordination fails. Nothing catastrophic yet, just unstable. 1 month after the cascade begins, the scale of damage becomes undeniable. 2,847 satellites destroyed, 342 satellites damaged but operational, 6,211 satellites maneuvered into higher orbits for safety, but now can't perform their intended missions. Internet speeds in regions dependent on satellite constellations drop by 60%. 3 billion people affected. Remote communities that relied entirely on satellite internet are now offline. Islands, villages, oil platforms, mining operations, weather stations, research outposts, all silent. Weather forecasting accuracy drops dramatically. The constellation of weather satellites has been shredded. Large regions have no coverage. A hurricane forms in the Atlantic. Without proper satellite monitoring, forecasters miss critical intensification. It strengthens from Category 2 to Category 5 in 18 hours. Coastal evacuations are rushed, incomplete. The storm makes landfall with inadequate warning. 1,400 people die who would have survived with proper warning. Wildfires in the western United States burn undetected for hours because fire detection satellites are offline. By the time ground reports come in, the fires are already massive. Agricultural monitoring collapses. Farmers who depended on satellite imagery for crop health and irrigation optimization are flying blind. Yields drop. 2 months into the cascade, governments are finally acknowledging this isn't temporary. Emergency legislation is passed. Space operations are nationalized in some countries. Military satellites are repurposed for civilian use where possible. Satellite manufacturers ramp up production, but building a satellite takes 18 to 24 months. Launching it takes scheduling, and even then, launching into debris-filled orbit is gambling with a $500 million satellite. The global economy contracts by 2.3% in Q2. Trade volumes drop 7%. The Kessler recession begins. Industries directly dependent on satellites, precision agriculture, logistics, maritime shipping, aviation, see immediate impacts. Others follow as cascade effects spread. 6 months after the cascade began, a new normal has emerged, grimmer, slower, more expensive. GPS works sometimes, in some places. Medium Earth orbit satellites survived better than low Earth orbit, but coverage is inconsistent, accuracy is poor. Logistics companies revert to older navigation methods. Efficiency drops 30 to 40%. Shipping costs increase proportionally. Global internet access has dropped by 25%. 3 billion people lost connectivity entirely or saw speeds reduced to unusable levels. The digital divide becomes a chasm. Urban areas with fiber infrastructure are mostly fine. Rural and remote areas dependent on satellites are information wastelands. Launch costs have tripled due to insurance requirements. Satellites need redundant systems, hardening, rapid maneuverability. Launch insurance premiums have increased 400%. The commercial space industry collapses. Small satellite companies can't afford the new insurance costs. Mega-constellations are paused indefinitely. Only government and military launches continue. The International Space Station remains abandoned. Without regular supply missions, its orbit is decaying. Atmospheric drag is slowly pulling it down. Current projections: uncontrolled re-entry in 18 to 24 months, unless someone can safely approach it for a boost. So how long till we can use low Earth orbit again? Optimistic estimates: 25 to 50 years for natural orbital decay to clear most debris. Pessimistic estimates: 75 to 100 years. And that's assuming we don't launch anything else that creates more debris. One major satellite failure or collision during the cleanup period, and we reset the clock. An entire generation will grow up
In a world where space is inaccessible, where satellites are rare and precious, where GPS is a luxury, not a utility, the immediate damage is estimated at $3 trillion. But the ongoing economic impact, lost opportunities, reduced efficiency, technological regression, could reach $10 trillion over the cleanup decades. Now, you might be thinking, that's worst-case scenario. It won't really be that bad. And you know what? You might be right. Maybe the cascade will be smaller. Maybe we'll develop cleanup technology faster than expected. Maybe we'll get lucky. But here's the thing about luck. Eventually, it runs out. We've been lucky so far. Thousands of near misses, collisions that didn't happen by coincidence of timing, debris that passed through crowded orbital shells without hitting anything critical. But every day we add more satellites, we're rolling more dice. And in probability theory, given enough rolls, you eventually hit every possible outcome, including the catastrophic ones. So the question isn't really, will Kessler Syndrome happen? The question is, can we prevent it before probability catches up with us? And that depends entirely on what we do right now, today, this year.
So let's talk about solutions, because despite everything we've discussed, the inevitable physics, the exponential growth, the economic catastrophe, we're not entirely helpless. We're just very, very close to being helpless. There's a window. Researchers call it the mitigation period. Right now, we're in it, but the window is closing. Current models suggest we have maybe a decade, 15 years at most, to significantly reduce the debris population before certain orbital shells cross the Kessler threshold permanently. 10 years. That's not a long time when you're talking about developing technology, implementing international treaties, and fundamentally changing how humanity approaches space. But let's examine what's actually possible, and let's separate the legitimate solutions from the science fiction fantasies. Solution 1. The laser broom. Concept is simple enough. Use ground-based or space-based lasers to vaporize small debris or ablate material from larger pieces to change their orbits. When you vaporize material from one side of a debris piece, the expanding gas creates thrust. Do it right, and you push the debris into a lower orbit where atmospheric drag will bring it down faster. It works, in theory, in labs, in simulations. In practice, requires enormous power. Atmospheric distortion affects accuracy, can only target objects at specific times and angles. Effective range limited, can only handle small debris. And here's the kicker. A laser powerful enough to vaporize orbital debris is also powerful enough to damage or destroy active satellites, which means it's basically a weapon, which means international treaties prohibit it, which means it's stuck in diplomatic hell indefinitely. Conclusion, technically viable, diplomatically impossible. Timeline, maybe 20 years if we get international agreement. Probably never. Solution 2. Net capture and tethered deorbit. This one's more mechanical. Launch satellites equipped with nets or harpoons, capture debris, attach a tether, drag it down into the atmosphere. ESA tested this in 2018 with Remove Debris. They successfully captured a test target with a net. It actually worked. So this is real, proven technology. The problem is economics. Each removal mission costs $100 to $200 million. You can capture maybe one, possibly two pieces of debris per mission. 34,000 tracked debris pieces, $150 million per removal. Total cost, $5.1 trillion. And remember, that's just the tracked debris, not the 130 million smaller pieces. Global space budgets combined, roughly $100 billion annually. At current funding levels, cleaning up all debris would take 51 years. But we'd need to be removing debris faster than new debris is created. And right now, debris creation rate exceeds our cleanup capability by several orders of magnitude. Conclusion, proven technology absolutely works, completely unaffordable at the scale required. Solution 3. Space tugs and robotic servicing. Instead of destroying or deorbiting debris, what if we could move it? Specialized spacecraft that rendezvous with defunct satellites and either repair them or push them to graveyard orbits. This exists right now. Northrop Grumman's mission extension vehicles have successfully docked with and moved satellites. MEV-01 docked with Intelsat 901. It works, it's operational. So why not scale this up? Launch a fleet of space tugs. Start clearing out the big dead satellites before they become collision hazards. Problems, each target satellite is different. Docking isn't standardized. Many satellites weren't designed to be serviced. You can't dock with a tumbling piece of debris. You need a cooperative target with docking ports and stable orientation. And again, economics. Each servicing mission costs hundreds of millions of dollars. There are 3,000 dead satellites. Do the math. However, and this is important, for high-value targets, this makes sense. There are about 50 defunct satellites that are particularly dangerous, massive, in crowded orbital shells, high collision probability. Remove those 50 and you significantly reduce the probability of a catastrophic collision triggering a cascade. Cost? $5 to $10 billion. That's within realm of possibility. Not cheap, but achievable if there's political will. Conclusion, feasible for high-priority targets, should be implemented immediately, won't solve the overall problem, but will reduce immediate risk. Solution 4. Passive deorbit systems. Here's a clever one. Attach drag-increasing devices to satellites before launch. When the satellite dies, deploy a large sail or balloon that increases atmospheric drag and accelerates orbital decay. Several companies are developing these. NanoRacks passive deorbit system, Tethered Unlimited's Terminator tape. The physics is straightforward. Increase surface area, increase drag, fall faster. A satellite that would naturally deorbit in 25 years might deorbit in 2 to 5 years with a deployed sail. The catch, this only works for satellites launched with these systems. It doesn't help with the 3,000 satellites already up there that don't have deorbit devices. But for future launches, this should be mandatory. Some jurisdictions are moving towards requiring it.
The FCC now requires satellites in low Earth orbit to deorbit within 5 years of end of mission. That's a step forward. Conclusion: excellent for future mitigation, should be mandated globally, doesn't solve the existing debris problem. Solution 5: active debris removal constellations. This is where it gets ambitious. Instead of one-off cleanup missions, launch a permanent constellation of debris removal satellites. Picture this: 50 to 100 specialized spacecraft distributed throughout LEO, autonomous systems, AI-driven targeting, constantly identifying, approaching, and removing or deorbiting debris. Each spacecraft could potentially handle dozens of debris pieces over its operational lifetime. Make them reusable, make them refuelable in orbit. At scale, costs drop dramatically. Instead of $150 million per debris piece, maybe $10 million, maybe less with mass production. The problem is upfront cost. Developing the technology, launching the constellation, you're looking at $50 to $100 billion minimum. And who pays for it? It's a global commons problem. Everyone benefits from clean orbit. No single nation or company wants to pay for everyone else's benefit. Classic tragedy of the commons. Everyone has an incentive to free ride. Everyone waits for someone else to solve it. The only solution is international cooperation and funding. A UN space debris removal program funded by all spacefaring nations proportional to their orbital usage. Status: discussed, proposed, negotiated, not implemented. Political will: insufficient. Conclusion: technically possible, economically challenging but feasible with international cooperation, politically gridlocked. Timeline: probably never without a forcing event. And that's the brutal reality of space debris mitigation. The technology exists or can be developed. The economics are challenging but not impossible. The problem is political will. Nobody wants to pay billions to clean up a mess everyone created together. So let's talk about what happens after disaster. Because historically, humanity is terrible at prevention but excellent at reaction. The Titanic sinks, suddenly we have international maritime safety laws. Chernobyl explodes, suddenly nuclear safety protocols become stringent. Fukushima fails, suddenly coastal nuclear plants face new regulations. So picture this: the cascade has happened. 2,847 satellites destroyed, $3 trillion in economic damage, low Earth orbit rendered unusable. The UN Security Council convenes an emergency session. For once, everyone agrees, we need to fix this. Within 6 months, a $200 billion International Space Rescue Fund is established, the largest peacetime technological mobilization in history. Debris removal technology development accelerates, mass production begins, launch cadence increases to unprecedented levels. Military and civilian space programs cooperate. Technology is shared. Patents are waived. It's treated like a wartime emergency. Over 10 years, thousands of removal missions clear the worst debris. Orbital shells become accessible again. New international treaties establish strict rules, mandatory deorbit systems, orbital traffic management, collision avoidance protocols, heavy penalties for violations. Total recovery timeline: 20 years. Cost: $500 billion. But it works. Except we paid $3 trillion in disaster costs first, plus 20 years of reduced space utilization, plus the economic opportunity cost. Preventing the cascade would have cost $10 to $20 billion. Responding to it cost $3.5 trillion. Brilliant, absolutely brilliant use of resources. But we're not there yet. We're still in the prevention window. So what actually needs to happen? Here's the actual solution roadmap. Not the ideal solution, the realistic one.
Step 1. Immediate, high-risk debris removal. Target the 50 most dangerous defunct satellites and debris pieces. EnvySat, Cosmos 1408 fragments, large defunct satellites in crowded orbits. Cost: $5 to $10 billion over 5 years. Funding mechanism: international cost sharing by spacefaring nations. Step 2. Mandatory deorbit systems for all new satellites. Global regulation requiring passive or active deorbit capability on every satellite launched. Timeline: 5 years from end of mission for LEO satellites, 25 years for GEO. Enforcement: orbital access denied for non-compliant satellites. Step 3: improved space traffic management, real-time conjunction assessment, automated collision avoidance, standardized protocols. Investment: $2 to $3 billion in tracking infrastructure and software systems. Step 4: active debris removal constellation development. Begin development of scalable, cost-effective debris removal technology. Pilot program: 10 satellite constellation to prove concept and economics. Investment: $15 to $20 billion over 10 years. Step 5: international treaty establishing orbital commons management, legal framework for space traffic management, enforcement mechanisms, liability frameworks. Status: long overdue, should have been implemented 20 years ago. Total cost for prevention: $30 to $40 billion over 10 years. That's 1% of the cost of responding to a disaster. So why hasn't this happened? Because nobody wants to go first, because the benefits are diffuse and the costs are immediate, because space debris is a problem for future us, and future us isn't here to vote. Meanwhile, we keep launching, keep adding satellites, keep increasing debris, keep rolling the dice, and eventually, statistically inevitably, we're going to roll snake eyes. Models suggest a 10% probability of a debris cascade event by 2035 under current trends, 25% by 2045, 50% by 2060. Those aren't comforting odds, especially when the cost of being wrong is $3 trillion and 20 years of recovery. So we're at a decision point, right now, today. Do we spend $30 billion to prevent a disaster, or do we wait, gamble, and hope probability doesn't catch up with us? Based on human history, we both know the answer. We'll wait, we'll gamble, and when the cascade happens, we'll act shocked, surprised. We'll claim nobody could have predicted this, despite all the warnings, despite all the data, despite knowing exactly what's coming. Because that's what we do, that's what we've always done. And somewhere up there, in that invisible highway 300 miles above our heads, 2 pieces of debris are traveling toward each other at 26,000 miles per hour. They don't know they're on a collision course, but they are.
Let me tell you about the satellite that never launched. Project Horizon, a telecom satellite designed to serve rural India. $450 million investment, hundreds of engineers, 3 years of development. Canceled in 2024. Not because the technology didn't work, not because the market wasn't there, but because insurance companies ran the orbital debris collision probability models and said, no, too risky, we won't insure it. Welcome to the invisible force already reshaping the space industry, the empire of necessity, the cold mathematical reality that makes certain things impossible, not through lack of technology, but through pure economics. Project Horizon isn't unique. At least 14 commercial satellite projects worth a combined $6.7 billion have been canceled or indefinitely postponed since 2021 due to debris concerns. The small satellite revolution that was supposed to democratize space? Slowing down. Startups can't afford the insurance. Investors are getting nervous. The boom is becoming a bubble. Launch providers built capacity for thousands of satellites per year, but launches are declining, not because rockets aren't ready, because customers are hesitating. Space industry growth rate, 2020 to 2021, 8.2%. 2021 to 2022, 6.7%. 2022 to 2023, 4.1%. 2023 to 2024, 2.9%. Projections suggest growth could go negative by 2027-2028 if debris concerns continue increasing. The second space age, the commercial space revolution, is dying before it really began.
not killed by technology failure, not killed by lack of funding, killed by orbital debris, by probability, by the accumulation of human carelessness now constraining human ambition. The orbital shells are being divided into actuarial categories: low-risk zones, mostly empty, high orbits; high-risk zones, crowded LEO shells; uninsurable zones, areas contaminated by weapon tests. Insurance premiums for LEO satellites have increased 147% since 2019. For specific crowded orbital shells, up 300%. At some point, the math stops working, when insurance costs more than the satellite, when collision probability exceeds acceptable risk, projects die. Except for the mega-constellations. They keep launching. Why? Because they're large enough to self-insure. They can absorb losses. If they lose 50 satellites to collisions, it's expensive but survivable. Small operators can't do that. One collision is bankruptcy. So they're priced out of the market. Result? Market concentration. The space industry that was supposed to democratize is instead consolidating. Only the giants can afford to play. And this is before a cascade. This is just from current debris levels and current collision rates. Imagine what happens after a cascade event. After a cascade, the commercial space insurance market would probably collapse entirely. Lloyd's of London has already indicated they might exit the space insurance market if debris collision rates continue increasing. Without insurance, commercial space essentially ends. Governments might continue military launches, scientific missions might proceed with public risk, but commercial satellites? Dead. All those plans for internet from space serving billions of people? Canceled. All those Earth observation startups monitoring climate and agriculture? Gone. All those logistics and transportation optimization services? Ended. And then, the economic impacts cascade through every industry that depends on space services. Precision agriculture depends on satellite imagery and GPS. Without it, crop yields drop 15 to 20%. Global food production decreases accordingly. Maritime shipping efficiency drops 30%. Supply chains slow down. Trade volumes decrease. Disaster response becomes less effective. Hurricane tracking less accurate. Earthquake damage assessment slower. Wildfire detection delayed. Climate science loses crucial data. We're flying blind on the most important challenge humanity faces. Military capabilities degrade. Not catastrophically, military systems have backup and hardening, but significantly. Strategic surveillance becomes limited. Precision weapons become less precise. The geopolitical implications are enormous. Nations that invested heavily in space-based systems lose strategic advantages. The global balance of power shifts. Unless one nation planned for this. Unless one nation built backup systems while everyone else relied on satellites. A nation with extensive ground-based backup systems, hardened infrastructure, less dependence on space. Some analysts believe this is why certain nations haven't been more aggressive about debris mitigation. If your adversary depends more heavily on satellites than you do, orbital debris becomes an asymmetric weapon. Not a weapon you use actively, just one you allow to happen through negligence. Every anti-satellite weapon test sends a message: we can deny you access to space, and the debris will hurt you more than us. It's area denial through pollution. Deny your adversary the ability to use space by making space unusable for everyone.
Mutually assured debris, the new deterrence doctrine. Except, unlike nuclear weapons where both sides are deterred by mutual destruction, debris weapons disproportionately harm space-dependent nations. The United States economy is approximately 3 to 4% directly dependent on space services. European nations, similarly. China, probably 2 to 2.5%. Russia, maybe 1.5 to 2%. The more advanced and space-dependent you are, the more vulnerable you are to space denial through debris. So the strategic incentives for debris mitigation are misaligned. The nations that could clean up orbit are the ones that benefit most from keeping it clean. The nations that benefit strategically from debris contamination have little incentive to help clean up. It's a perfect prisoner's dilemma. Cooperation benefits everyone, but defection benefits the defector even more, at least in the short term. So, we're stuck. Economically stuck, strategically stuck, diplomatically stuck. While operators perform 30,000 collision avoidance maneuvers per year, while insurance premiums increase, while the debris population grows. But there's one more force at play, one that might actually change the equation: public awareness. Right now, almost nobody knows about orbital debris. It's not in the news, it's not part of public discourse, politicians don't campaign on it. Google search volume for space debris effectively zero compared to other environmental issues. Public concern level? Non-existent. But what happens when there's a major collision, when satellites start failing, when GPS goes down for a week? Suddenly, everyone cares. Suddenly, it's a crisis. Suddenly, politicians are forced to act. This is how environmental regulation happens, not through scientific warnings, we've had those for decades, through disasters that make the problem visible and immediate. The Exxon Valdez wasn't the first oil spill, but it was the one that was televised. Public outrage forced regulatory change. The first major collision that disrupts services people depend on, that's the Exxon Valdez moment for space debris. After that, political will appears. Funding materializes. International cooperation becomes possible. Which brings us to the paradox. We probably need a disaster to prevent a catastrophe. We need something bad enough to get attention, but not so bad it triggers an unstoppable cascade. A minor collision that destroys a few satellites and disrupts GPS for a few days, that might wake everyone up. A cascade that destroys thousands of satellites and makes orbit unusable for decades? That's too late. We need the warning shot, the near miss that becomes a close hit. And statistically, we're probably going to get it. Models suggest a 40% probability of a significant collision event, destroying 5 to 20 satellites by 2030. 15% probability of a severe collision event, destroying 20 to 100 satellites by 2035. 5% probability of a catastrophic cascade initiation by 2035. We're rolling the dice every day. Eventually, we're going to hit the number. The question is, do we wait for the disaster and respond reactively, or do we prevent it proactively? History suggests we'll wait. We'll need the disaster to force action. But maybe, just maybe, if enough people understand the risks, we can change that pattern. Which means the question becomes, what do you do with this information?
Let me show you something beautiful. This is the view from the International Space Station, the most beautiful view in the solar system, astronauts say. Earth from space. Clouds and oceans and continents and the thin blue line of atmosphere protecting everything we've ever known. But turn around, look the other way, and you'd see, if you had the right instruments, a shell of debris, thousands of dead satellites, millions of fragments, all moving at orbital velocity, all potential bullets. From a distance, Earth looks like Saturn now, a beautiful planet surrounded by rings, except our rings aren't ice and rock, they're junk. This is what we've done in 68 years of spaceflight. We've surrounded our home planet with a cloud of garbage moving at 17,000 miles per hour. And the sick irony? That garbage is now preventing us from leaving. Every mission to the moon has to pass through the debris field. Every Mars mission, every deep space probe, they all have to run the gauntlet of orbital garbage we created. Collision probability for a Mars-bound spacecraft passing through LEO? Currently about 1 in 5,000. After a cascade? Could be 1 in 50. We're building a prison around our own planet, a prison made of our own technological debris. So let's be clear about what's at stake here. This isn't just about satellites. This isn't just about GPS and internet and weather forecasts. This is about whether humanity gets to be a spacefaring species, whether we expand beyond Earth, whether we have a backup plan if something catastrophic happens to our home planet. Because Earth isn't perfectly safe. Asteroids exist, climate is changing, pandemics happen, supervolcanoes are real. Our long-term survival as a species might depend on becoming multiplanetary, and that requires access to space. But if we trap ourselves with our own debris, if we make orbit impassable, we've guaranteed humanity stays on this one planet forever. Or at least for the next century while the debris clears. And a century is a long time when you're talking about existential risks. A lot can go wrong in 100 years. So here's where we are, right now, today. We have maybe a decade to significantly reduce orbital debris before certain orbital shells cross the point of no return. The technology to fix this exists. The economics are challenging but feasible. The knowledge is there. What's missing is political will, public awareness, international cooperation. And that can change. If enough people understand the stakes, politicians listen. If enough constituents demand action, budgets get allocated. If enough nations feel pressure, treaties get signed. It's happened before. Ozone depletion, nuclear test bans, whaling moratoriums, problems that seemed unsolvable until public awareness forced action. This is the next one, the orbital environment, the space commons. So what can you do? Talk about it, share this information, make it part of public discourse. Contact representatives, support space sustainability legislation. Support organizations working on space debris mitigation, the Space Foundation, Secure World Foundation, European Space Policy Institute. If you're a student, study this. Become an engineer or policymaker focused on space sustainability. We need people working on this. If you work in the space industry, prioritize sustainability. Advocate for deorbit systems. Support cleanup initiatives, even when it costs more. If you're a policymaker, make this a priority. Fund debris removal. Mandate satellite deorbit capabilities. Support international cooperation. And if you're just someone who uses GPS and streams videos from space-based internet, understand that those services depend on maintaining the orbital environment. Because here's the truth. This is a solvable problem. $30 billion over 10 years prevents a $3 trillion disaster. That's a 100-to-1 return on investment. That's the best deal in risk management. But the window is closing. Debris is accumulating. Collision rates are increasing. Probability is catching up with us. We don't have another decade to debate this. We don't have time for perfect solutions. We need good enough solutions implemented immediately. The people who can make this happen know who they are. The question is, will they? I can't predict the future. Nobody can. Maybe we'll get lucky. Maybe we'll dodge the cascade for another decade or two. Maybe technological solutions will emerge faster than expected. Or maybe 6 months from now, a piece of debris hits a satellite, which creates more debris, which hits another satellite, which triggers a cascade we can't stop. And the difference between those futures, the choice between them, is being made right now. By decisions made today, by priorities set this year, by actions taken or not taken. We've surrounded our planet with a shell of debris. We've created a potential disaster that could cost trillions and trap humanity on Earth for generations. But we also have, right now, today, the knowledge and resources to prevent it. The question is, will we? Will we spend $30 billion to prevent disaster, or wait for disaster and spend $3 trillion responding? History suggests we'll wait. Probability suggests we'll eventually lose the gamble. But maybe, just maybe, this time can be different. Maybe enough people will understand the stakes. Maybe political will can be generated before the disaster. Maybe we can be proactive instead of reactive. I don't know. I hope so.
because I'd really like to see humanity become a spacefaring species. I'd like to see us expand beyond Earth, explore the solar system, reach the stars eventually. The alternative, trapping ourselves on one planet because we couldn't clean up our orbital backyard, would be the most pathetic end to the space age imaginable. So that's the story. That's the situation. That's what's at stake. You now know what most people don't. We're in a race against probability. We're playing orbital roulette, and the chamber's filling with bullets. What you do with that information is up to you. But somewhere up there, right now, at this exact moment, a piece of debris is traveling through space at 17,000 miles per hour. And maybe, just maybe, it's heading towards something important. Unless we choose to prevent it.